Right now, somewhere in the universe, a star 20 times the size of our sun is collapsing inward. In less than a second, it crushes itself into an object smaller than a city, but with gravity so violent that not even light can run fast enough to escape it. And here's what nobody tells you: that's actually the boring kind. Welcome back. Today we are going down a rabbit hole, and I mean that almost literally, into the most extreme objects the universe has ever produced. Black holes. You've heard the word. You've probably seen the blurry orange photo. But what most people don't realize is that black hole isn't one thing. It's a family of monsters, each one stranger, more violent, and more terrifying than the last. By the end of this video, you're going to understand every major type of black hole science has discovered or theorized. What they are, how they form, how big they get, and why some of them might be even weirder than the universe has any right to be. Well, let's start from the smallest and work our way up to something that will genuinely break your brain. Here's a question most people get wrong. How small can a black hole be? The answer is roughly the size of Lahore, maybe 20 kilometers across. But it would weigh more than 3 of our suns. 3 solar masses, crammed into something you could theoretically drive across in 15 minutes. Let that sit for a second. These are stellar black holes, and they're the most common type we know about. They form when a massive star, something at least 8 to 20 times the mass of our sun, burns through all its nuclear fuel and has nothing left to fight gravity with. What happens next is called a core collapse supernova, and it is one of the most violent events in the known universe. The outer layers of the star explode outward in a shock wave bright enough to outshine entire galaxies for weeks. But the core has nowhere to go but inward. It collapses under its own gravity until it crosses what physicists call the Schwarzschild radius, the point of no return. The event horizon forms. A black hole is born. Now here's where it gets interesting. Stellar black holes range from about 3 solar masses on the low end to roughly 100 solar masses on the high end. The biggest confirmed stellar black hole we found is called Cygnus X-1, sitting about 7,000 light years away, and it clocks in at around 21 solar masses. But the strangest thing about stellar black holes isn't their size. It's what they do to the space around them. If you were somehow orbiting one at a safe distance, you'd actually survive just fine. The gravity at that distance is no different from orbiting any other star of the same mass. The danger isn't the size of the black hole. It's getting close to it, cross the event horizon, and according to general relativity, you don't immediately feel anything dramatic. You just, can't come back. You've passed the point where escape velocity exceeds the speed of light. And from that moment forward, you are on a one-way trip to the singularity. We'll talk about what a singularity actually is in a moment. Because first, we need to talk about something that was for decades purely theoretical, until it wasn't. For years, astronomers had a problem. They could find small black holes, stellar ones, and they could find absolutely colossal ones. But there was a gap in the middle, a gap so suspicious, so conspicuous, that some scientists started to wonder if the universe was hiding something. They were right. Intermediate mass black holes, or IMBHS, sit between 100 and 100,000 solar masses. They're the awkward middle child of the black hole family. Too big to have formed from a single dying star, but too small to be the behemoths sitting at the centers of galaxies. So where do they come from? This is still one of the most hotly debated questions in astrophysics. The leading theories involve runaway stellar mergers. Essentially, in dense star clusters, stars collide and merge faster than they can die, building up a supermassive object that eventually collapses. Another theory suggests they form from the direct collapse of enormous gas clouds in the early universe, before smaller structures like individual stars had time to develop. For a long time, finding one was like hunting a ghost. We had hints, strange X-ray sources in the outskirts of galaxies, gravitational signals that didn't quite fit, but nothing definitive. Then, in 2020, LIGO, the gravitational wave detector, caught the signal of two black holes merging. One was 66 solar masses, the other 85. The result, a black hole of roughly 142 solar masses. The first confirmed intermediate mass black hole created in real time, detected by ripples in space-time itself. Think about that. We didn't see it. We felt it, a distortion in the fabric of reality, washing over Earth like a ghost wave, detected by an instrument that can measure a displacement 1,000 times smaller than the width of a proton. The universe is not subtle. It's just very, very far away. Every large galaxy in the known universe, every single one we've looked at closely enough, has one of these at its center, including ours. Right now, 26,000 light-years from where you're sitting, there is a black hole with a mass of 4 million suns. It is called Sagittarius A star, and it has been there since before Earth existed. Supermassive black holes are the titans of this world. They range from millions to billions of solar masses, and they sit at the gravitational heart of virtually every major galaxy we've ever observed. They don't just passively exist there. They shape everything around them. The distribution of stars, the rate of star formation, the fate of the entire galaxy. All of it is influenced over billions of years by the monster at the center. The most extreme example we've confirmed, the black hole at the center of M87, a giant elliptical galaxy 55 million light-years away. It weighs in at a staggering 6.5 billion solar masses. In 2019, it became the first black hole ever directly imaged, that famous orange ring of glowing superheated gas orbiting the event horizon. The image took the combined computing power of telescopes across the entire planet and years of processing to produce. And what we got was a blurry orange donut. But that blurry orange donut represents humanity looking at one of the most extreme objects in existence. The event horizon of M87's black hole is larger than our entire solar system. Here's what nobody talks about enough, though. If you were somehow falling into a supermassive black hole, a truly massive one, the tidal forces at the event horizon would be so spread out over such an enormous distance that you might cross it without feeling a thing. You wouldn't be shredded. You wouldn't even know you'd crossed it. You'd just be inside, and the universe behind you, due to extreme time dilation, would appear to fast forward. Stars would be born and die. Galaxies would evolve. Billions of years would pass in the outside universe while you fell in what might feel to you like hours. You'd be a ghost watching the end of time. Now, what if I told you that supermassive isn't even at the top of the ladder? Scientists have a separate category, not officially standardized yet, but increasingly necessary, called ultramassive black holes. These are black holes exceeding 10 billion solar masses, and a handful of them have been found that push even beyond that. The current record holder, a black hole called Cygnus X-1, located about 10.4 billion light-years away. Its mass, approximately 66 billion solar masses. Its event horizon has a radius of about 1,300 times the distance from Earth to the Sun. The entire orbit of our solar system could fit inside this thing's event horizon multiple times over. Cygnus X-1 isn't just a black hole, it's a quasar, an object so luminously violent that the matter swirling into it releases more energy than the combined output of the entire Milky Way galaxy. Hundreds of billions of stars outshined by one object that is, at its core, the ultimate drain of the cosmos. How does something get this big? That's the terrifying part. We're not entirely sure. They must form incredibly fast in the early universe, consuming gas and merging with other black holes at a rate that our current models struggle to fully explain. It's one of the most active areas of research in modern astrophysics. The universe had a violent childhood. And Cygnus X-1 is the scar. Everything we've talked about so far formed from matter we can trace. Collapsing stars, merging galaxies, feeding frenzies of gas. But what if some black holes formed before any of that? Before the first star ever ignited? Before atoms had even fully organized themselves? Primordial black holes are theoretical objects that may have formed in the first fractions of a second after the Big Bang, when the universe was an almost unimaginably dense, chaotic soup of energy. In that environment, quantum fluctuations, tiny, random variations in density, could have been large enough that regions of space collapsed directly into black holes, with no star required. Here's what makes them genuinely unlike anything else. Primordial black holes could theoretically come in any mass. Some might be as light as an asteroid. Others might have grown into the supermassive black holes we see today. They would be cosmic fossils, carrying information about the very first moments of existence. And here's the kicker that keeps physicists up at night. Primordial black holes are a serious candidate for dark matter, that mysterious substance that makes up 27% of the universe's mass energy content, that doesn't emit or absorb light, that we can only detect by its gravitational influence on everything else. It might, in part, be a population of ancient, invisible, city-sized black holes scattered through the cosmos. We haven't confirmed this, but we haven't ruled it out either. And the search for primordial black holes is one of the most exciting frontiers in physics right now. Here's something that will ruin your sleep. Most black holes aren't sitting still. Every star that ever formed was spinning. When it collapses into a black hole, conservation of angular momentum, the same principle that makes a spinning ice skater faster when they pull their arms in, causes the black hole to spin extraordinarily fast. We call these Kerr black holes, named after the mathematician Roy Kerr, who solved the equations in 1963. A spinning black hole doesn't just have an event horizon. It has something called an ergosphere, a region of space just outside the event horizon, where space-time itself is being dragged around like water in a whirlpool. In the ergosphere, it is physically impossible to remain stationary relative to the outside universe. Space is rotating, and you rotate with it. You can't fight it. You can't hover. You go around whether you like it or not. But here's the wild part, the Penrose process. If you were to enter the ergosphere and cleverly split an object in two, one part falling into the black hole and one escaping, you could actually extract energy from the black hole's rotation. You'd leave with more energy than you came in with. The black hole slows down slightly, Physicists have proposed that the most energetic jets of particles we observe shooting out of active black holes, jets that stretch for millions of light years, may be powered by exactly this mechanism. The black hole is, in a very real sense, losing rotational energy to the universe around it. Then there are Reissner-Nordstrom black holes, charged black holes. These are more theoretical because in practice a charged black hole would rapidly attract opposite charges from surrounding plasma and neutralize, but mathematically, a charged rotating black hole, a Kerr-Newman black hole, contains something almost science fictional, a ring singularity. Instead of a point of infinite density at the center, the singularity stretches into a ring, and some solutions to the equations suggest that passing through the center of that ring might lead to somewhere else, a different region of space-time entirely. We have no way to test this. The outside of a black hole is, by definition, hidden from us. But the math doesn't lie, and the math says the inside of a rotating black hole is one of the strangest places that physics is even capable of describing. We've been using the word singularity this whole video. Let's finally confront what it actually means. At the center of every black hole, at the end of that one-way fall, general relativity predicts a point where density becomes infinite and volume becomes zero, a singularity. A place where the equations of physics don't just give extreme answers, they give undefined answers. The math breaks down completely. Most physicists believe this means general relativity is incomplete, that a true theory of quantum gravity, which we do not yet have, would describe what actually happens at the center of a black hole in a way that doesn't require infinity. Stephen Hawking and Roger Penrose proved mathematically that singularities are an inevitable consequence of general relativity. But Hawking also spent the later part of his career arguing that black holes aren't as permanent as we think, that quantum effects cause them to slowly radiate energy over unimaginably long timescales, eventually evaporating entirely. This is Hawking radiation. It has never been directly observed. It's far too faint for our instruments. But theoretically, every black hole is slowly dying. The smallest ones die fastest. Stellar black holes will outlive the current age of the universe by an almost incomprehensible factor. But they are mortal. Even the titans will eventually go dark. One by one, over timescales that make the current age of the universe look like a blink. So let's zoom out. Black holes aren't one thing. They are a spectrum of cosmic extremity. From the stellar remnants forged in stellar death, to the ancient relics of the Big Bang, to the incomprehensible ultramassive engines spinning at the hearts of galaxies a billion light years away. They are the universe's most honest statement about what happens when gravity wins. And in every single case, whether it's 3 solar masses or 66 billion, the rules are the same. Cross the horizon and there is no going back. Not for a matter, not for light, not for information. The universe keeps its secrets well. If this video changed how you think about space, hit subscribe. We go deep on this stuff every week, and drop a comment below. Which type of black hole freaks you out the most? Personally, primordial black holes. The idea that dark matter might just be ancient, invisible, city-sized black holes hiding in the galaxy around us is something I genuinely cannot stop thinking about. See you in the next one.